Chemistry. I know all these are waiting and dying for this stuff. All right. This is a reaction that you gotta have memorized. You're gonna see this for the rest of the semester, and when you get into nursing, wherever you're gonna go, you're gonna see this over and over. It's dealing with acid-base stuff, and it's a big concept, and unfortunately, or commonly, it's also a big nuisance for a lot of nurses and a lot of teachers teaching. And I had believe it or not, I had to tutor a nursing instructor on how to present this at the other school. So I put it all together for her, and it worked out well. It worked out well. She did very well with it. So this is not an easy subject to learn, let alone teach. All right. So I'm not going to go into heavy things with you in lab. That's not the purpose here. But when you do this stuff, there's a whole chapter in your book about fluids, electrolytes, acid, base. Expect to put more time into there. There's a lot of chemistry. But this should get you started with it a little bit. This is called the carbonic anhydrase reaction. So let's put it up here so you can see what's going on. Carbon dioxide will mix with water to make an acid called carbonic acid, and that will dissociate into hydrogen ions and bicarbon ions. Now I'm just going to abbreviate bicarbon ions by just calling it bicarb. All right, that's how I'll say it. So carbon dioxide with water will turn into an intermediate called carbonic acid. The enzyme that's going to do this is carbonic anhydrase. If it ends with ASE, it's an enzyme. Sucrase, lactase, maltase, okay, amylase. If it ends with ASE, it's an enzyme. If it ends with OSE, it's a sugar. Glucose, maltose, lactose. Okay? When you get into that with the digestive system, that'll help you. Okay? We're not talking about carbohydrates here. Carbon dioxide mixes with water. It turns into an acid, but it's a very weak acid, and it doesn't sit there for very long. We're talking about a split second. And immediately dissociates into ions. Hydrogen ions and bicarbonate ions. Okay? This is a reaction that's all over your body. We'll see it in the blood-brain barrier, which you should have learned from A&P1. You'll see it in the stomach. That's how you make the hydrochloric acid. They take the hydrogen from here and they make it into hydrochloric acid. It's in the pancreas. We'll be using the bicarb to neutralize the acid that's going into the intestines. It's in the red blood cell. We got to change the carbon dioxide into this acid, and it floats as an ion throughout your whole body, in your blood rather. You also see it in the lung because we have to turn it back from the ion, bicarbon ion, because that's how CO2 kind of sits in our bloodstream. And we got to turn it back to a gas, so we can breathe it out. We can't breathe out ions, okay? And it's in the kidney too. If the hydrogens get too high over here, your kidney can spill it out. So you're going to see this all over the place, okay? Now, the key thing over here is that, and I'm just going to erase this right here, but the key thing over here is that there's going to be a balance. 50% of the products are over here and 50% are over here. And the reason why it can do that is because the yield signs go both ways. You see, if I actually put hydrochloric acid, which is a strong acid, it will turn into hydrogen ions and chloride ions. 100% of this will turn into ions because the arrow only goes one way. It's irreversible. So you will get zero. If you put this in water, you'll have 0% of this, but in the water, you'll get 100% of this. It's 100% dissociated into these two ions. That makes this a strong acid. And these ions look for opposite things. You put your hand in there, you've got a lot of ions on your finger. These things will start eating away at your fingers. That's why it's a strong acid. Now, is that clear about that? Now, this is a weak acid, carbonic anhydrase. And what happens here, we don't see it in this phase for a very long time. It goes from here over to here, but it has to still go through this step. But they're both reversible. Carbon dioxide, when mixed with water, will turn into hydrogen ions and bicarbonate ions. But you will have 50% of it here. So you will have 50% of it over here, and you will have 50% over here. It's a teeter-totter. It balances. If I put more hydrogen in here, this goes up, so the reaction is going to go this way to make it go back to 50%. If I put more carbon dioxide in this reaction, the reaction is going to go this way to get it back to 50%. It's a buffer. So let me show you what's going on in real life so that you could see this. I'm running a marathon. Okay? Running a marathon. And then all of a sudden, after about 2 miles, well, in my case, after about 1 minute, I get this pain. Ah! That pain is from what substance that's being made? Lactic acid. Okay? Stuff you learn from AMP1, muscles and stuff. But you get lactic acid. That's going to put more hydrogens in your system. Right? So theoretically, this 50% is going to be 70%. Just give me your number. Which means this will go down to 30%, so that we keep the 100% there. So what's going to happen here? We got to get rid of these hydrogen ions because we want it back to 50-50. We've got to keep it as a teeter-totter. So the hydrogen ions have to leave, and we got to do that fast. Now the first thing that's going to happen as a defense mechanism is you're going to have this reaction going on. That's only good temporarily. We're talking about seconds temporarily. We've got to get rid of this. So if we increase this, does the reaction want to go to the door or to the window? To the door. Does that make sense? The reaction goes this way. It's going to turn back to carbonic acid, and then you're going to make a lot of CO2. How do you get rid of CO2? Exhale. So when you're running a marathon, are you breathing like this? Are you breathing? You're breathing faster to get rid of that CO2 until this balances. Does that make sense? Okay? That's what's happening here. Okay? Until it balances. And that'll keep on going until you stop running the race, because you're going to keep on making more hydrogens up here. Okay? Questions about that? Let's talk about, just to make sure you understand this, let's talk about somebody who's got emphysema. All right? Normally, you have 50-50 here. Now, a person with emphysema has to walk from here to the door. That is like walking 20 miles for a person with emphysema. And they are going to produce lactic acid very fast. So this is going to go up. So let's say 70%. The reaction wants to go to the door or to the window? To the door. Good. All right? So that it goes this way. Now normally, you would be able to blow off all this CO2. But a person who's got emphysema, you're not going to be able to do that. They have problem exhaling. So what's going to happen to the amount of CO2 in a person's blood? It increases. Now this is going to go up to like 80% or so. Which way does the reaction want to go? To the door or to the window? To the window. The reaction goes this way so that we could try and get this to 75. It won't ever, because this is always going to be occurring. So what happens to the amount of hydrogen in a person's blood now? Does it increase or decrease? Increases. So now they're increasing, and they have a condition called acidosis. When you increase hydrogens in the blood, they have a condition called acidosis. Because it's due to a respiratory reason, we call it respiratory acidosis. Okay? Now, how do you get rid of ions? These water-soluble things. If they get too high, how do you... We know that to get rid of CO2, what organ's going to do that? Lungs. What organ's going to get rid of ions? Kidneys. Now, kidneys do work good, but they take a long time. This may take minutes to do, whereas the kidneys will take minutes to hours to do. But they're going to work overtime because a person who's got emphysema is always going to be pushing it towards this way. So this is where you probably didn't think about it, but the lungs and kidneys work together. And it's the physiology of the lungs and kidneys that kind of disturb a lot of students. Because there's a lot of chemistry in there. If you have lung disease, your kidneys will compensate. If you have kidney disease, your lungs will compensate. If you have kidney and lung disease, you're screwed. So if you become a nurse and you get a patient in an ICU that has lung and kidney disease, tell your nurse supervisor and say, this is probably all I need. Don't give me any more patients. This will keep me busy throughout the next 8 or 10 hours. Because you got to keep up with this. You're not that you're screwed, but this is where in a person who's got lung and kidney disease, because the hydrogen keeps on going up, they're going to have to be put on dialysis. They're going to have a kidney outside of their body to get rid of this hydrogen, let alone potassium and other things. All right, does this make sense? Okay? So, this is everything I just explained. So regulation of pH, you got lung, it's going to compensate or regulate the partial pressure is CO2. You guys learn about partial pressures? Or you will when you get into respiratory. You're going to see it quite often. So if you hyperventilate, you're going to blow off more CO2. If you hypoventilate, you're going to keep more CO2. Okay? So what this is saying here is that if you, before you get into this, if you increase CO2 in your body, what happens to your pH? And here, right, but what happens to the pH? Does it go up or down? It goes down. If you have too much CO2 in your blood, your pH goes down. Look it. If the CO2 increases, and you can't blow it off, it's going to go this way. What happens to the amount of hydrogens in your body? Increase. If the hydrogens go up, what happens to your pH? It goes down. So when a person who's got a lot of CO2, their pH goes down. Okay? And that's what it's saying over here. If your PCO2 goes up, the pH goes down. If the PCO2 goes down, your pH goes up. It's not about memorizing, it's about understanding it. You memorize, you're going to get some questions right, but if you don't understand it, you're not going to get everything right. You've got to understand the concept here. All right? So renal regulation, it can control the pH by how much bicarb leaves or how much hydrogen leaves. For instance, I can make more bicarb leave, then does that mean net-wise, do we have more hydrogens in our body? If we have less of this, when you compare it, sure. So that's why the kidney could have control about that. We could make this excrete out of the body, or we could decrease, or if we excrete this out of the body, then this is going to it's going to increase the pH, right? If I put more of this in the body, then net-wise, this is going to be less than. Does that make sense? And that'll also increase the pH. And that's what's going on with all this. That's why the kidney's really where it's nice because it puts everything together. I love the kidney on that. It puts all the stuff from endocrine, all the stuff you learn from A&P1, it all comes down. It all puts it all together. Chemistry and calcium, all the stuff. All right? But that's what makes it a little bit tougher, is because you got to go back to all this other stuff to make sure you understand it. All right? So this is just showing you with the reaction up here, the lungs and the kidneys.